How is everything going?
Oh, it's going okay. Trying to get everything finished right
Is everything in control?
now. I think so, for the most part.
I think these are the times when you get too overwhelmed, I suppose. And
Yeah.
you're taking quantum, correct?
Yes. That's the class that's really dragging me down. It's just tough stuff.
Yeah, that's it. Yeah. First of all, the subject is hard. And yeah, Dr. Bird is very demanding. I think he keeps high standards. Yeah, very
Yes.
good. So I think homework 11 due date is back done, and now it's homework 12, I suppose, right? And I'll make it due for 20th Tuesday.
Mhm. Yeah, I haven't finished the homework 11 yet.
Yeah, but I think you're finished homework 10. That means you're pretty much catching up.
Yes.
So that's very good.
I'll be all caught up this week.
That's good. So I haven't posted this yet. Very quickly, homework 12. So actually, before that, I should actually have this wrong. April, we'll make it due April 22nd, which is the Thursday. And I should say that April 20th, which is Tuesday, I will not be able to have class. So for that, today I might really try to finish it off. I usually finish this in two lectures, so hopefully I'll finish this off today. So maybe I'll either jump steps or you usually allow time extra, so we'll see. Okay, so I'll keep this class and final exam date. I don't have it yet. Yeah. It's on the website, I suppose. On the website, I have updated it, the final exam date, but I have not copied it here, so I don't have it immediately. But I'll let you know. Usually by this time I start writing it down. Okay. Next time it will be better, in better order.
I'm sorry, do you know the last day of class?
It's April 30th.
Okay.
April 30th is the last day, so that's a Friday before the exam week.
Okay.
And May 7th is the last day of exam.
Okay.
And yeah, 7th is a Friday. April 30th is a Friday.
Thank you.
So do you plan to go home, like all that? Typically, what do you do? Like,
Well, since like I'm trying to still have my apartment here.
yeah,
So I'm trying to make some money through the summer, either by doing the quarter-time TA position.
That's
or
perfect.
trying to get into some research.
Have you talked about it to Dr. Palapatra?
Dr. Talapatra, yes, I've talked about the quarter TA time, and he said that, they will do it this summer, they just don't know much about the positions or like time, how many people need it, so he said he's just gonna find out last minute, and that's just how it is, so.
But keep him informed that you're interested. Keep the communication channel very clear.
Yes.
Because as you heard, like it is at the last moment, so clarity is an important factor. If you show any confusion, then since the decisions will be taken very quickly.
Yes. I'll like remind him that I really am interested.
Yeah, because that's much easier, or that's much more productive than you trying to work outside. Nothing wrong in it, but it's just that it's much easier because this will be physics. It will be much more productive for you. So yeah, you should. And do you know who you're going to work with? You did mention.
I'm talking with Dr. about research.
Okay,
We have a meeting today about some stuff, so hopefully that's when I'll be when we'll talk about maybe some research funding or something.
Yeah, if that can be worked out, that's really good. And again, make it clear that if you're ready for even partial assistance, those are all ways of, because this much money might be too big.
Yeah.
This much. Usually everyone aims for giving full funding. No one, I think it's no one wants that precedence, I suppose, that partial funding, because then people start assuming that, partial is sufficient. So it has good and bad things partial, at least give me something rather than nothing,
Right.
But then that leads to the idea that, in the future, people expect only partial.
Yeah.
I don't have any, this is just a friendly advice I'm giving. It is nothing to do with what's available in the department.
Right.
Yeah. And I don't know much. Yeah. Okay. So we talked about Kepler orbit, and we want to talk about precession. Hope the spelling is correct. Is this correct spelling? Do you happen to know?
Yes.
Of the perihelion. Struggle. So the idea is that let me define. We have shown that the energy of the Kepler orbit is half mv square minus g m1 m2 over r. So that's potential energy plus kinetic energy. So kinetic energy plus potential energy, because potential energy is negative for gravity. We showed that you can write this as in terms of r and phi. Oh, sorry, I should say this is mu, right? So that mu is 1 over mu is 1 over m1 plus 1 over m2. So this is mu times r dot square, how the radius changes with time, plus of mu r square phi dot square, how the angle changes with time, minus g m1 m2 over r. So let me write this as alpha over r. I've used alpha is g m1 m2. Correct. So that's energy. If you want, we immediately see that the angular momentum, so which is mu r square times phi dot, is a constant, which we call is angular momentum. So that's a constant. You can do a couple of things. The moment you have this, I can replace this phi dot with Lz and R. There's one more thing I can do. This is dr by dt. I can replace time with phi, because phi is the monotonous function of time. So talk in terms of phi jot instead. So let's do that algebra. So this is E is equal to right. Let me go slow here. So this is 1 by 2 mu r dot square, and this comes out to be plus. Then I substitute this in here, so that is LZ squared over 2 mu times r raised to 4, or r squared, and minus alpha over r. And that leads to the idea that this is an effective potential in R. So you define so a few things it was about. So let's define effective potential to be LZ squared over 2 mu R squared minus alpha over R. And this effective potential can be plotted in this manner. So it's your R. For small r, the first term dominates. For the large r, the second term dominates. And there is a nice interpretation here. That's your R naught. And this quantity here is your U naught. And this is U effective. R naught then comes out to be equal to LZ squared over mu times alpha, and U naught is equal to alpha over 2 times R naught, which is a negative, minus alpha over 2. That's your two integral. So there are these two constants we will use to write the whole thing. So if we were to write like range in those terms, so let's do this. So this is, let me say this is 1 by 2 mu r dot square, and I can put an alpha here, alpha there. So that's gives me plus alpha here. So that makes it an R naught, alpha R naught. So this is up here. So this is alpha over 2 R naught times R naught square, R naught over R whole square. So I just added, multiplied and divided there. And this is minus alpha over R naught times R naught R. It's just standard Kepler problem we're working. Let me do one more step here. I want to process this first term also. So notice there is this alpha over R naught, which is actually U naught here. This is also U naught. So let me put that also as U naught. So maybe do that in a separate place and bring back. Since you're in the classroom, it's easier. Otherwise, I cannot switch boards like this. Okay, so we have this 1 by 2 mu r dot square, which is the same as half mu r by dt square. That's the same as 1 by 2 mu d phi by dt square times dr by d phi square. I changed the dt chain rule basically. I think to remove this, then it's much more transparent there. Right. So that's equal to 1 by 2 mu d phi by dt square is using angular momentum conservation, Lz square over mu square times r raised to 4, and that's dr by d phi square. So that's the same as there's an r square. So let's write this as so that's Lz square over mu times 1 over r raised to 4 r d phi the whole square. Put an alpha here, put an alpha there, so that makes it r naught. It's 1 by 2 r naught alpha over 2 2 1 over r raised to 4. Put an r naught now. Oh. Yeah, so alpha over, so this is alpha over 2 r naught times r naught square over r raised to 4 times dr by d phi. So that again gives you that u naught, so that coefficient comes in the front. So this whole problem of Kepler problem can be summarized as, if you want, as energy is equal to alpha over 2 r naught times r naught square over r raised to 4 r by d phi plus alpha over 2 r naught, or actually pull this all out, right? This is r naught over r the whole square minus of 2 times r naught over r. That's nothing but u naught minus u naught actually. So E over u naught is equal to minus r naught square over r raised to 4 dr by d phi the whole square plus r naught over r the whole square minus 2 r naught over r. Let's add a 1 here on the right side, and let's add a 1 on the left hand side also. Okay. And that identifies that this was a constant we introduced, that was eccentricity, remember? So eccentricity and let me check that because sometimes I have problems with the sun. Yeah, minus, right? What's the problem? Alpha, so it's 1 minus u naught. Oops. Yeah, I want to have this the following manner. So that's when I put in a negative sign here, right? I want to just pull the e over alpha over r naught. That's better, and then I keep the sign. That's okay, so this is plus minus. Yeah, so this is correct. I think anyway I made a mistake of not changing the sign. I think now it's correct. So what I did is I just divided it by alpha over 2r naught, right? And then I added 1 on both sides. That's all with algebra. So this is the same Kepler problem we're doing, but I'm doing it in a very short manner because we want to be able to do something more to this. We want to change, we want to perturb this. So E square was defined as 1 plus E over alpha over 2 naught, which has this feature of U naught showing up there. So this is the same as 1 minus E over U naught. So that's your E square. So let's see what we can do with this. So that's E square, write it in that form. In fact, take it on to the other. So this is E square minus, so this is a complete 1 plus, 1 minus R naught over R the whole square. So this is 1 minus R naught over R the whole square is equal to R naught over R square dr by dy. So when I take the square root, this reads R square dr over R square, and bring this in the denominator. So that's 1 over, or maybe I should write this on the left. It's better. So this is d phi is equal to R naught dr over R square, and it's 1 over E square minus 1 minus R naught over R the whole square. Okay, that's our starting from the energy, we got how the angle changes with R. Right, this is the idea of the orbit. Correct. So let's now define what do we mean by precession of perihelion. So the precession of perihelion is going to be defined as oh, maybe I should yeah. So we should remember that our minimum in an let's define our minimum to be E over 1 plus R naught over 1 plus E, and our max to be R naught over 1 minus E. Correct? And what are these quantities in here? This is your orbit. That's your angle phi, that's your R, that's your R naught. And this is your R minimum. And this is the point where you get an R maximum. If it was a perfect elliptic orbit, that's what you get. And that's your R minimum to R maximum. And we know that this is governed by that. So we are assuming that. So this is R naught over 1 plus E cosine phi. Right? In principle, there's a phi minus phi naught, but I've chosen this to be having the minimum and maximum value at phi equal to 0. Right? Okay, so my precision would be, so let's actually evaluate how far you go, where does the angle go from? So start from our minimum and go to our maximum. Okay. So notice that it's a symmetry in the orbit. You go from here to there, phi goes from 0 to pi, and then you come back to the same point. if I do this 2 times, I expect to get 2 pi. So I go from here to that pi, again I come back, so I'm expected to get 2 pi. So, and then I subtract the 2 pi out of that. Okay. That I will define is my precision of the perihelion, which I can define as delta phi. Is that clear? Exactly what we are doing. And using our relation, we have this would be equal to minus 2 pi plus 2 times d phi is going from, so this is r goes from r minimum to r maximum. So let me actually put this correctly. So this is r naught over 1 minus e, r naught over 1 plus e, and we have naught dr over r squared times 1 over e squared minus 1 minus r naught over r whole square. We want to do this integral, so let's substitute quantity. So let's substitute 1 minus r naught over r to be equal to e cosine theta. This theta should not be confused with phi, but actually it is the same parameter, but this is a substitution variable. When we substitute this, we clearly see that minus r naught, actually plus r naught over r squared, dr is equal to minus e sine theta d theta. This derivative gives you a plus, this gives you a minus. So delta phi, the precision of the perihelion, takes the form minus 2 pi, which is what we have to subtract. So we expect this to be 2 pi, and that's a subtraction of minus 2 pi. So that's plus 2 times, actually, I should also do this, right? So what is the value here? If I put r is equal to r naught over 1 plus e, so then our minimum is 1 minus, and r is, that's 1 plus e is equal to e cosine theta. So that means 1 cancels out, so that's minus e is equal to e cosine theta. That implies that theta is equal to pi. And R max is 1 minus e is equal to e cosine theta, which gives you plus e is equal to e cosine theta. That implies that theta is equal to 0. So those are the limits of the integral. So let's substitute them there. So the precision is given in terms of minus 2 pi plus 2 times. When it is minimum, that's pi, and as maximum it is 0. R naught over r squared is minus e sine theta theta. And this is this whole thing is 1 over e squared minus e squared cosine squared theta. The denominator and the numerator exactly cancel. E sine theta in the denominator also. So they cancel out. And what you get is minus pi, right? So minus sign. So this is exactly equal to 0. So this is minus 2 pi plus 2 pi is equal to 0. Is that very clear what I did? Right. So, which is what is expected if it's a pure Kepler problem. That means to say if it is G M1 M2 over R, there is no precision, right? That should be exactly 0. Okay, that's very good. But we want to now change it. So we go back now, and we are going to add something to this, and again do the same calculation and try to see what's the precision. So is that clear, the motivation? Okay, so we go back and write our energy. So we go back to our energy. E was equal to half mv square, or sorry, mu, right? Mu v square minus g m1 m2 over r. And I'm going to add something to this. I have a choice of keeping it attractive or repulsive. Let me say I want to keep this very generic. So I'm going to see minus and kappa. Kappa is going to be a very small parameter. The idea is that if I make this very strong, then I have to redo the whole problem. But if I keep this very, very tiny, like 1 in 100, then I can say whatever solution I have must be correct. And this is going to be a small correction to that. So we're going to keep small perturbations. So this is called a perturbation in quantum mechanics. It has been popularized a lot. So this is called perturbation theory in general. So we're going to put a kappa there. I want to have the dimensions of energy. So I'll keep kappa dimensionless. And let me have this to be U naught. So this is a constant, right? So let me say this is alpha over 2 R naught. This is a constant, nothing to do with the potential. And the potential itself, I keep it very arbitrary. And I say that it has to have this form. Okay, so this is some potential which is dominated by 1 over R potential. Okay, this could be 1 over R, this could be 1 over R squared, this could be 1 over R cubed, this could be tangent, exponential of 1 over R. Everything is fine. Okay, is that clear? What's the perturbation we are making? And kappa is where the parameter comes. I'm going to say that kappa is very much less than 1. So that means kappa over this energy is very much less. So between these two, the magnitudes, that's decided by that. So that's a model we are having. And we'll keep that generic and at the end do some analysis, or at least have a result in terms of F, which will let us do whatever we want with it. So the same procedure can go through. The whole idea was that here R naught over R played an important role. So we want to keep that. So all this will go through, and we will be able to write energy will be equal to alpha over 2 R naught times, exactly like earlier, we will be able to say this is R naught over R square times dr over d phi, the whole square, minus or plus actually, right? R naught square plus R naught over R the whole square minus of 2 times R naught over R, and the new term here, which is plus, sorry, like it will have the same sign as this, so this is minus kappa of F R naught over R. Is that clear? Again, do the same idea. Divide by R naught, add a 1 to it, so that so this becomes 1 plus E over alpha over 2 R naught. That's E square. We are going to identify that as our old solution, R naught over R square, E R over E phi whole square. Plus, I've added a 1, so I have to add a 1 here. So that's 1 minus R naught R, the whole square, and then there is minus kappa R naught. So this becomes, I'm again going to, I'm interested in d phi. So this is b phi. So this is equal to E square. Right? So R naught. Let me write one more step before I start processing. So this is E R by E phi whole square is equal to E square minus 1 minus R naught over the whole square plus kappa. Take a square root, get the d phi on one side, and what we have is d phi is equal to naught R over R square, and this is 1 over E square minus okay. So that's prepares us for calculating the precision, and you would do my delta phi would be equal to, so delta phi would be going from minimum to maximum and then minus 2 pi, right? So I write the minus 2 pi first. That's plus integrate from R naught over 1 plus E to R naught over 1 minus E, and then do the same idea, right? R naught R over R square times 1 over E square minus at this stage, one has to be careful. So this is a trick here. If you were to proceed, so this seems to be very similar to what we had earlier. So do the make the same substitution and proceed. And it turns out that if you go that route, you come across a divergence that doesn't really exist. Okay. So you will encounter an infinity, especially because we will be throwing away stuff, right? When we are doing a perturbation, it seems like an unnecessary, we call it a pathological infinity in the sense it's because we are perturbing it, it leads to some constant getting thrown away and we are getting a divergence. So one has to be careful. So just for that purpose, one has to use this trick, which seems unnecessary at this point, but there's nothing wrong in it. So you'll use the identity that this is a 1 over something quantity. So let's notice, make this observation that if I were to take the derivative of the square root of E square minus 1 minus R naught over R plus kappa times F of R naught over R. So that's a derivative I can do. And notice that where does my eccentricity show up in this whole square root business? There is nowhere there is eccentricity except in the first term. So that's a simple derivative I can do. And in the left hand side, let me also include 1 over E. So there is a 1 over e to begin with, and then I take the derivative of a square root begins with a 1 by 2, and then changes the power to 1 by 2 minus 1, so that goes to the denominator. So that's e square minus 1 minus r naught over r the whole square plus kappa f of r naught over r. Right? And then I have to take the derivative of the argument, but there is only e squared in the first term, so that's 2 times e. But I divided that e for that purpose exactly. This e cancels that e, and that's 2 cancels that. And that allows me to recognize that this 1 over square root of that whole quantity is actually the derivative of the same square root in the numerator. So my precession of the perihelion, plus 2 pi, let me write that plus 2 pi, so that I can write it on the right side, is equal to r naught over 1 plus e, r naught over 1 minus e, and that is naught r over r square, and I have 1 over e derivative, and now the square root is in the numerator. Still very general as far as the perturbation goes, except for the fact that we assume that is of the form r naught over r, like there's an angular dependence in there. If I want to do this integral, it is convenient only if I can take the derivative outside this. And the question comes, can I take the derivative outside? And one should be careful. Notice this is an integral in r, so this derivative doesn't really care for r, right? So this can come out of the integral, but then you realize that, oh, this actually depends on the limits. So there is a derivative on the limits there. So we have to take care of that. So let's call this r max, which depends on e, and let's call this r minimum, which depends on this e. And so we have to actually take care of that. So let's proceed to that. So this is equal to, so let's delta phi plus 2 pi is equal to, so this time I'm actually forcibly taking this out. So I made an error now, right? This is not allowed because the limits actually depend on e. Not r square and the square root. So this is e square plus, oops, minus. Good. But that's not okay, because this has to hit on this. So I'm going to subtract that. So whatever is the error I have made, I'm going to subtract that. So the question is, what do I get if I were to hit it? So if I were to hit on this, so there are 3 places where there is e. Here's e, e, e. When I hit on this, that's my answer. So whenever I hit on this, I have to subtract that out. So that's minus of 1 over e d by dE of this quantity r naught, so which I have called it the r max, right? And when I hit that r max, that's derivative of r max of r minimum to let me write this as R naught over 1 plus e to R max. That's R naught ER over R squared and the whole square root. Is that okay? We'll ask this in a minute. So this is 1 over e d by de. There's one more I have to do the minimum also, right? Our minimum. That minimum is this, and that's maximum. So chain rule, and do the same thing. This time I'll write the top one, and this I'll write as our minimum. Right? So that I recognize the variable. Okay. So that's a general expression at this point. Any questions at this stage? Yeah.
You can't do R max and R min at the same time. You have to do it one or the other.
Yes, because I had hit this on this, 3 terms, right? First, this hits on this can hit on this, and this can hit on this.
I see.
So those are the 3 terms, but these are all supposed to be on the left-hand side, right? But instead, I said that, okay, I'm supposed to hit only on this, right? So I subtracted those 2 things. So let's say, yeah. So here is a question general. So suppose you have d by dx of, let's say, some constant c to x of dy f of y. What is that equal to? So this comes out to be exactly equal to f of x. Okay, and why is that? Right? So we'll show that. So how that comes about is that, remember your derivative idea, change this by dx. So derivative is limit delta tends to 0 of whatever is here, c x plus delta dy f of y minus of c to x dy f of y divided by delta. Correct? Is that clear? So f of x plus delta, usually we just do the derivative of a function, but this is add a quantity, subtract it out, and then divide by delta. Correct? So this is now integral. So if I were to add this, this is a tiny increment. So I'm doing an integral now of a function. First I go from c to x, right? This is in direction of y. And then I increase it a little bit. So this is x plus delta. Right? This is the change in the numerator. First I go from c to x, that's this quantity. Then I go from c to x plus delta. So the increment I'm making is this tiny rectangular element there, right? Area of that rectangular element. And then I'm saying that I want to divide it out by this base of the rectangular element, which will leave me with the height of the rectangular element, which is a function f of x, which you can show this by doing that. Oh, this is nothing but 0 to delta dy f of y divided by delta. And the limit delta tends to 0, that's exactly equal to f of x. Sorry, f of, so this is x to delta, x to x plus delta. And that's f of x. Is that clear geometrically? And that's the idea of integration. That's a fundamental theorem of integration, if you want. That derivative is the anti of integration. Right? The derivative is anti of integration in this sense. Right? So, or let's put this as a quiz. Right? So this is a quiz. Demonstrate this or write something about that. Right? Write your thoughts on that, so because that's a fundamental quantity there. Okay. Okay, so using that, we can actually evaluate these derivatives. It's straightforward, correct? We just said that I just have to evaluate it at that point. So delta phi plus 2 pi. I'll leave the first one as it is. We'll come back and evaluate that. So this is R naught over 1 minus E, R naught over 1 plus E. This is E R over R square, square root of E square, minus 1 minus R naught R whole square, plus kappa. Wow. Okay. That's equal. And the second term here, so let me do the derivative of R max. Right? So that's minus 1 over E. Derivative of R max is, so help here, so this is minus 1. Minus 1 R naught over 1 minus E the whole square, and then take the derivative of 1 minus E, so that's a minus 1 again. So minus signs cancel out. And take the derivative of this, so that what that leaves us is that R naught over R square, but I'm evaluating at R max. Right? So this is R max square. And this is square root of E square minus 1 minus R naught over R max squared plus kappa f of R naught over R max. Is that clear? And the next term is minus 1 over E. So this time it will be minus 1 R naught over 1 plus E, right? So this is our minimum. So this is 1 plus E the whole square. And there is no sign difference here. And this time I do R naught over R minimum square. Times E square minus okay. So at this point, we know everything, how to do everything. You can do this integral here, but first let's process this. Since you're here, I can actually do it on various poles and get back. Correct. So let me evaluate this square root separately, this term separately, and this term separately. Okay. So let me go back to 5. Yeah, so let's space that. So let me evaluate the second term. So that's minus 1 over E. the 3 minus signs, so that's minus. So that's R naught over 1 minus E is R max. One of them cancels out. Is there a simple way of doing this? Notice that, yeah, so actually, let me do this. R naught over R max everywhere is equal to R naught over R naught times R max is 1 minus E. So that's just 1 minus E. So wherever I see R max, I can just put, or wherever I see R naught over R max, I just can put 1 minus E. So then the second term there equals, so it's minus 1 over E, 1 over so there's 1 minus E there already, and R naught over R max is 1 minus E again, that cancels out. And then I have square root of E square. It's minus R naught over R max is 1 minus E, that cancels out, so that's E square cancels out. And that's plus kappa of F of 1 R naught over R max is 1 minus E. So this whole thing is equal to minus 1 over E. E cancels out, how much is this? 1 minus 1 over E times kappa times F of 1 minus E. That's significantly simpler in that form. The second term, we will use R naught over R minimum is equal to R naught over 1 plus E, that's equal to 1 plus E. Do that same thing for the third term now. That's equal to plus 1 by 1 over E, right, plus 1 over E, and then there is 1 over 1 plus E. One of them cancels out, R naught over R is 1 plus E again, that cancels again. And then we have square root, again, 1 minus 1 minus again makes it E squared, so this is E squared minus E squared plus kappa F of 1 plus E this time. So whatever that function is, evaluate it as plus and minus. So that's 1 over E kappa F of 1 plus. Is that clear? So, so we have only one integral remaining then. So let's write this, collect them all together. Oh,
I'm sorry, I missed the negative. How does the negative get to a positive?
because there are only two signs here, right?
Oh, I didn't, I'm sorry, yes.
Right,
Thank you.
there's two here on the top, there are 3 of them. So, seems like if I put this all together, delta phi plus 2 pi is equal to, this is just 1 over E square root of kappa times whatever the function I'm dealing with, evaluate it at 1 plus E, the dimensionless quantity, right, minus of 1 over E, evaluated at 1 minus E. Presumably this would be a tiny effect, but still that's sitting there. And the next integral, we know how to do this, right? But let me write that down first, plus 1 over E. There's one integral remaining, but you probably know how to do this. because Kepler problem has the same thing. Okay, with me? Okay. So okay, so to do this integral, we'll again substitute 1 minus, so substitution is 1 minus r naught over r is equal to e cosine theta. Right? So that r naught dr over r square is equal to minus e sine theta d theta. Right? Same substitution as we did for the Kepler, original Kepler problem in the beginning. So that's equal to then. So 1 over e kappa f of 1 plus e minus 1 over e kappa f of 1 minus e. And let me try to squeeze this whole thing in here, plus 1 over e by dE. When I have r naught over r the minimum here, so minimum is 1 plus e, so that's minus e. So this is theta equal to pi. So this is theta equal to pi. And the top one will be 0, right? Because then it is 1 minus e, that becomes a plus, so theta is equal to 0. This is minus e sine theta, theta, and this whole thing in the square root will be equal to e square, and then there is e cosine theta, so that's again e square sine square theta plus kappa f of r naught over r is 1 minus e cosine theta. Right. Until now, we didn't have to use any of our expression for f, and even the perturbation as of now completely exact, right? We have not made any approximation until this stage. Here is where we do the perturbation. We say that we do the square root, or actually let me go one more step, right? One more step here. So let me take out the e sine theta and really make this explicit. So this is 1 over e kappa f of 1 plus e. Minus 1 over e kappa 1 minus e, and plus I do this derivative eventually after I get the result. So that's 0. I changed the limits to 0 to pi and pretty much pull out e sine theta. So this is 0 to pi d theta. E square sine square theta, and then square root of 1 plus kappa f of 1 minus e cosine theta divided by e square sine square. So this is where the perturbation comes in. We are going to expand this square root and keep only the leading order because kappa is small. Square root of 1 plus x for small x, you need to keep only the first term. And that's the approximation, and that's the perturbation we are talking about. So let's where should I put this in? I think I can. It was this. Yeah. I could have gone to the other board, but then you need to capture this in the camera. Okay, so that's equal to expand that as a series. So let's do phi plus 2 pi is equal to 1 over e kappa f of 1 plus e minus 1 over e kappa of 1 minus e. Expand that as a series, so that leads to plus 1 over e of e 0 to pi d theta e square sine square theta. And I expand this, it is 1 plus 1 by 2 of this quantity. So the first term will be 1 by 2, and the second term will be equal to 1 by 2. So it's 1 over e. That's 0 pi d theta e square sine square theta times 1 by 2 of kappa times f of 1 minus e cosine theta divided by e square sine square theta. And that's the key feature in here, that this could have diverged, right? At theta equal to 0, this goes to, if not for the sine square theta coming in the numerator, this could have gone to 0. And here it actually exactly cancels out, and we don't have such term. So these two cancel out. And there are higher order terms which we don't keep. That's that. Let's evaluate this integral separately and put that back in there. Change that. So what is that integral? So 0 to pi d theta sine square theta. That's equal to so sine square theta is 1 minus, so this is d theta, 0 to pi sine square theta is 1 minus cosine 2 theta divided by 2, correct? So that's equal to pi by 2 minus of 1 by 2 of sine 2 theta, integral of sine 2 theta divided by 2 going from 0 to pi. So that's sine of 2 pi, 0, that goes to 0, right? This doesn't contribute, that's equal to pi by 2. Oh, I messed up. Okay. So this is pi by 2, good. Okay. So that's equal to, so then if I substitute this in there, but that's a small mess up I have made. I will fix that. So putting this back in that integral gives me, so this is this is pi by 2, then derivative of this gives me a factor of 2, that cancels, so that gives me a pi. So what I have is pi plus 1 over e kappa f of 1 plus e, and minus of 1 over e times kappa f of 1 minus e. and this whole derivative here, so it's 1 over e d by e and 0, and that's kappa over 2 can come out. So plus kappa over 2 times 0 pi of d theta of f of 1 minus e cosine theta. So that's all. If I give this form, then I can do that integral. But I said I made a mistake. So can I erase this part? Okay. So let's go back all the way. Where did I do this? Yeah, it was 2. Oh, something. Not so. Okay. So if you notice, I think you'll have to use your notes. There was this factor of 2 in there. So we were going from R minimum to R max and then multiplying by 2 to come back. Right? So there was this factor of 2 involved in here. And when we erased this part, right, we missed that 2 because this should have been 2 pi. Right? If I put kappa equal to 0, I should get back my 2 pi, which will cancel this, and this is my change in delta pi. Right? So we missed that factor of 2 all through. So I had to put that all everywhere. Okay. So if I were to put that in there, so there is a factor of 2 in here. So a factor of 2, which will bring in a factor of 2 here, factor of 2 there, and it keeps going. Right? It's pretty much put a 2 everywhere. So let's circle those 2's that added. 2, 2. Right. Did I confuse too much?
No.
That's bad actually. I should have been careful. And if I were to put that 2 in here, so this comes the 2 there, 2 there, 2 there, and 2 here. Right? So 2 cancels out. So this is 2 pi then. Factor of 2 here, that's 2, 2, and that's a factor of 2. Okay. Cancels the 2 pi there, which gives the correct limit that in kappa tends to 0. There should be 0. So this should be 2 over e times kappa 1 plus e minus 2 over e kappa times f1 minus e. 2 cancels out and plus kappa times 1 over e, derivative of e, and do the simple. This is a simple integral if I provide you with the function f. So that completes the calculation actually, because this is all one can do without specifying your f. Right? But let's do a simple example where there is an f. Right? So let's say that the perturbation that we put in, remember, was f of r naught over r, because kappa times alpha over 2 r naught. Right? So there was this energy, and you put in a perturbation. Let's have a simple perturbation where f of x, f of r naught over r is simply square of this, which will make it a cube, right? This is already an energy, right? So then you're putting in, let's make it a cube, right? R naught over r cube. I can put any structure I want. So this is cube. So I'm having a cubic potential as a perturbation. That's what we can have it any power in principle. Right. So this or should I make this simple? Right? Yeah, let's make this. Yeah, if it's cube, then I have to do this cube function. Right? Let me make this a square. Let's have a square. Square will be easy. So that means f of 1 minus e cosine theta will be equal to, I just have to put this as 1 minus e cosine theta the whole square. So 0 to pi of d theta f of 1 minus e cosine theta for our specific case. So this will be equal to 1 minus e cosine theta squared. So that's 0 to pi d theta 1 minus 2e cosine theta and plus e squared cosine square theta. Great. First term gives you a pi. Cosine theta going from 0 to pi is 0 because it starts from 1 and goes to minus 1. This doesn't contribute, so that's plus e squared and integral of 0 to pi cosine square theta. But that is exactly like sine square theta, that gives you pi by 2. That integral is pi by 2. So, and we should also have f of 1 plus e. F of 1 plus e is 1 plus e squared. Correct? 1 plus e will be 1 plus e squared. And so delta phi would be equal to 2 over e square root of kappa times 1 plus e squared. Take a square root of that, that's 1 plus e. And then there is minus 2 over e square root of kappa, and is 1 minus, and plus kappa over e time derivative, derivative with e of pi by 2 pi plus e squared times pi by 2. This term doesn't contribute because derivative with respect to e is 0, so this doesn't contribute. This gives you a 2 times e cancels out, 2 cancels out here. So that's pi exactly there. So that's equal to, and here also there is a cancellation. The first term cancels out, and it's the second term that comes in. So 2 kappa e, and so it is 4 times square root of kappa. E cancels out, and this is plus 2 cancels out, so it's kappa times pi. Here. So, okay, there you go. So, yeah, perfect. Okay.